Diffusion, the international science radio show.
Okay, well, hello. My name's James Vandeleur. I'm a physics PhD student at the University of New South Wales here in Sydney. Um, I have spent a lot of time, obviously, learning, but also teaching physics, and I enjoy sharing the excitement of physics with others.
Thank you, James. So, James, it's the International Year of Quantum Science and Technology. So, what does that mean?
Well, it's very exciting. I think I think most important is that it means that there is this international recognition of how exciting quantum is. Um, we're also roughly 100 years since the start of quantum. It's one of those things that it's almost impossible to say exactly what was the start of quantum, but roughly 100 years. Um, so it's very exciting. And I think quantum has been a bit of a buzzword in pop science for a little while. Um, and so I think it's a really good opportunity to jump onto that excitement and sort of lift the curtain and help people understand really what it means.
So, it was the United Nations that declared the International Year of Quantum, I think.
Yes, it was. Um, yeah, and then it's been picked up by, so the Australian Institute of Physics is doing a lot with it in Australia, of course. Um, you could sort of consider them something like the local leaders, if you will. But it's quite a broad thing. I mean, there's lots of events throughout the year, and um, there has been and still is a big sort of call out for just anybody who wants to put on some sort of quantum related event can join the movement, which I think is
And
really cool.
if we were to, for people that weren't sure, would you have a quick, sort of simple definition of what quantum means? The
Ah,
word.
so yes, I think uh, quantum just means discrete energy. So the word quantum comes from quantization or a quanta, which is a discrete packet of energy. And you get discrete energy when you're either at uh, really small or really big energies. You see these quantum effects.
Yeah. And we teach a tiny bit of this in sort of HSC physics, as I recall. If they still do, it's been a long time since I was there. I know we did a little bit of the double slit experiment and things like that.
Mhm. Mhm.
Did
Uh,
you're
yeah.
more closer to the school times than I was. Do they still teach it?
Yes, yeah, we did. So I don't know whether we did double split in school, but we did sort of the typical example is a harmonic oscillator. So you have a
Mhm.
think like a spring would be the classical system, a mass on a spring or a pendulum even.
Mm,
Uh, and then if you quantize that, you get just like a sound wave on it. So if you have a string on a guitar, a
mm.
sound wave, the fixed sort of wavelengths, you get the same thing for a pendulum when you look at this sort of quantum picture. I remember doing that in school.
Because I think the lesson they were trying to get across to us when we did our basic double slit, we went from sort of water waves and sound waves going through slits to be able to visualize the wave part, and then you might have marbles for the particle interpretation. And it's like, well, light and other things, it turns out almost everything is not a wave or a marble or a particle. It's quantum, which is properties of both of those things, but totally different.
Yes.
It's its own
Uh,
thing.
it is its own thing. It's one of those very tricky things um, to describe. I think a nice way is I like to think of everything as a wave, and then a particle is an approximation for when you have a particularly fancy word is a localized excitation. But, you imagine a sheet and you've got a little ripple that's just this small bit. You can say that looks like a particle.
And isn't that funny? Because so you're from a particle physics specialization within physics, and
Hmm.
you deal with very high energy sort of events. But it's called
Yeah.
particle physics, but you don't believe in particles.
Yeah, yeah, it's one of those things. I believe in the maths and I understand the maths, and then whatever words you want to put on top of that, is always up for debate.
Because it's a little bit different than they teach it in some other things. So that's become, is that part of quantum field theory? That it's all waves,
Yeah,
everything's waves of fields, and then the actual excitations, the manifestations of the field, if you like, that interact with matter, are the particle effects or the
yeah,
quantum.
yeah, exactly, exactly. That's a great way to look at it. And so when we have the standard model of particle physics, which has all the different particles,
Mm,
you could think of that as all these different fields,
yeah.
sort of like different fluids that have these quantum fluctuations. Yeah, exactly right.
Yeah. So that's something extra for people, I guess, of because when I learned my quantum physics long, long time ago at university, that wasn't the way we were looking at it, and I suspect it's a little bit different interpretation in different parts, different specialities of physics,
Hmm.
because it's almost like, well, from a traditionalist, education that I would have had a long time ago. It's almost like you're saying, well, you just said it's all waves, which denies the wave particle duality, it would seem, but of course that's not really what you're saying at all.
Yes, so as with everything in physics, it depends on the problem you're looking at as to what's going to be the best model to think in terms of.
Mm,
Yeah, yeah, this is true. And like, when quantum started, it was very much this idea of a particle. It was really sort of Einstein who won his Nobel Prize for the photoelectric effect, which a lot of people don't realize, which basically you have a capacitor, two metal sheets, and you shine light on it, and it induces a current. And the details of that we can go into if you want. We don't have to, but
mm,
basically, Einstein came to the conclusion that light has to be in these discrete packets of energy called quanta, and so that was the particle, the photon.
mm.
And then quantum field theory requires special relativity, at least. So that actually didn't come till much later in
Yeah,
the,
yeah.
in the
And I mean
history
that's
of.
one of those things. So on the one hand, you've got that photoelectric effect that Einstein got the Nobel Prize for, which is the basis for things like solar panels and cameras and so
Yeah,
much
yeah.
modern technology. And then, as you say, you've got all the other consequences of all of these sort of different interpretations of things. But special relativity being in there is interesting because general relativity and quantum physics contradict each other's predictions a little bit, but they're both proved right by experiment. So we have a little bit of a paradox that hasn't been
Yes.
solved yet.
Yes. I mean, this problem is exactly one of energy scale,
Mm,
where if you're at a small energy scale, quantum is the right picture. If you're at a big energy scale, general relativity is the right picture. And you can do them together. You can
mhm,
do these sort of hybrids, but there are problems. There are mathematical problems.
mm.
There are signs that it's not a healthy theory when you do that.
This
So
is
this
one
is
of the exciting things about physics, isn't it? That it's not finished, that there's a
that's right.
lot to be
Yes.
discovered.
Yes.
Mm,
Yeah, and this was one of the funny things when we look back at, the end of the 1800s. They did think that physics was finished. They thought, we've got it all. We know how steam engines work. We know how electricity works. We can do everything.
it's got one little
Oh,
problem.
yeah, 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 black body radiation,
That's
something,
right.
something, something. We'll sort it out. And then 100 years later, it's a whole new field.
Well, that's the thing. So I think physics is one of those areas of science, more so than maybe some others, where physicists are trying to be wrong in their experiments, that they really want new
Hmm.
physics because we know that relativity is incomplete and we know that quantum is incomplete, and particularly around gravity, which goes
Yeah.
into astronomy, of course, and Big Bang Theory, and the predictions we make don't match what we see in the sky, and we haven't completely figured out all the reasons. So we want new physics, and that means a lot of physicists actually want to be wrong.
Yes, well, I mean, it's funny you say that. Almost every talk, as a particle physicist, almost every talk I go to goes along the lines of, here's the standard model. We all know that. We know it has these problems. So I'm going to introduce a beyond standard model, a new physics, a new particle, and then, crank the handle, do the maths, and see what it predicts.
Mm.
And one of the problems we have is that we have lots of beautiful theories that are all beyond the standard model that could all be right, and we're just waiting for a sufficiently high energy collider to come along and tell us which one is the correct one. So yes, you're right. There's a lot of yes, how wrong can we be and exclude things in our
Yeah.
search for the right.
And of course, the irony, I can't remember who pointed this out in one of the books I was reading, that Big Bang Theory used to be when it was first became a area of study in universities, like in 70s and so. It was the cheapest possible way to do science because it was pencil and paper, and then
Mm.
gradually it became more complicated as they progressed, and then it got to the point where you needed high energy physics to be able to test some of the predictions. So particularly in the quantum field. So you needed to start doing big particle colliders and things like that. And you end up with the most expensive machine in the history of the world to prove what used to be the cheapest way to do physics.
Yes, yes. Although I will say that um, we're now at a stage where so the future colliders, the next generation of experiments they're proposing, are about the same cost as some of the big astrophysics experiments, like the
Mm.
James Webb Telescope and these things, which is just a consequence of, I think ultimately we've gotten better at making magnets, I think is what it comes down to. But yeah, so while that certainly is true, well, was true for CERN, it's much less so now, which is really exciting for particle physics. It makes our cell a lot easier.
People were talking about desktop particle accelerators with these improved magnets and things. Did that ever take off?
Ah, well, I've never heard of that. So
Ah,
not hugely.
worth Googling.
I'll have to have a look. That sounds kind of cool. Um, yeah,
No, you haven't
there,
come across it.
yeah, I haven't come across it. No. I
And
would be surprised though. I mean, you need
mm,
the advantage of a right, because you build a magnet and then that has some force. So that's a constant
mm.
acceleration. So then the bigger your ring, the longer time you have to apply that acceleration. So I'd be surprised if you can do a real desktop collider. But I'll have a look. That sounds
Yeah,
interesting.
yeah, yeah. Maybe they weren't. Well, I'm not. I don't recall what the intention was going to be, whether it was experimental or whether they thought they were going to get some sort of device out of it.
Right,
I'll have
right.
to. I'll have to now cover that on a future show. It's just one of those memories that came up of things I'd read about lots of times. So
Yes,
if
right,
we go
right.
back to quantum technology, I don't think most people, because it was such a buzzword, as you were saying, like before AI became the buzzword that got your stock to go up, it was quantum was everything, and all the mystics got
Yes.
onto quantum as well. But quantum technology's been in everyday life for a long time.
It has. It has. And this is something people often forget. Um, and particularly with quantum computing, we don't have a quantum computer in the sense that the computation is still classical, but the device is quantum, right? The silicon semiconductors, the reason we can build transistors that are now limited basically by electron effects. So they're as small as we can make them with current
Mm,
technology, and that's quantum. That requires understanding of um, these so-called uh, Fermi levels and conduction bands where your electrons fill up positions, and because it's all
mm,
discrete energy, there are certain energies they are allowed to be, and then you get these sort of 1-0 effects, and that's how you build modern computers.
mm,
Um, but also, so that sort of comes from what we call condensed matter physics. Um, from my side of physics, or particle physics, when we built the collider, we have all of these sort of spin-off technologies. Um, superconducting magnets being one of them, which lets us build MRI machines,
Mm.
which have been around for quite a while now too. And you know, these are obviously terrific things for humanity and keeping us happy and healthy. Um, what were some other things? I had some things written down. Spectroscopy. Yeah, that's the other thing.
Hmm.
So if we go back to this idea of quantum being discrete energy,
Hmm.
and then in an atom, of course, you have the nucleus in the middle, you've got the electrons around the edge, and those electrons can change their energy level.
Mm.
But it has to be discrete, so it's always a known amount that they change by. And when they do that, they absorb or spit out a photon, some light. And so if that energy jump is always the same, then every atom has a fingerprint of these energy jumps um, that it emits.
Mm.
So this is a spectroscopic analysis that you can do that chemists love because they can have some sample of something and they can shine a laser at it and see what comes out,
Mm.
and they can know exactly which atoms are in that sample.
It's pretty
Um,
powerful stuff, isn't it?
it's incredibly powerful stuff, and it allows you to do incredibly precise stuff because these steps are known. And a very similar mechanism allows you to make atomic clocks, which now define well, have for a while defined the SI second, the standard unit of a 1 second.
And the discovery of the spectrum goes back to Isaac Newton.
Uh, well, yes, certainly the discovery that light can be split into a spectrum. Yes, absolutely. And then it's, you know, only a few hundred years later, and you now have the precision to measure that spectrum much more precisely, and the
Mm.
knowledge of um, what these discrete bands mean. Yeah.
Yeah, and in astronomy, they use it to know how much of different elements are in the sun and in distant planets
Mm,
around other stars and all
of
sorts of things.
course. Yeah, yeah, yeah.
Mm.
Yeah, that's right. Oh, it's just it pops up everywhere. And you know, as I said before, we're about 100 years of quantum now, and so
Mm.
it's not this new thing. It's this well-developed, well understood thing.
And that's one of those limits with modern computers, is my understanding, is that we used to think with Moore's law that we'd just get smaller and smaller and smaller transistors. And there's people that have developed single atom transistors, but generally we're now going for multiple cores instead of one tinier and tinier core with more transistors because we're hitting up against quantum noise that's getting in the way.
Yes. Yes, exactly. So I mean, this problem you have is quantum tunneling.
Mm.
Um,
Now, can you explain that simply?
so physicists would use the word a potential, right? But you can imagine, and it's actually surprising how accurate it is to imagine just a hill or a
Mm.
valley. And so if you happen to have two of these valleys next to each other with a little hill in between, and you put a ball somewhere in your system, then that ball will roll down. And depending on where the ball starts,
Mm.
it might get stuck in one of the valleys, it might have enough energy to go over. Right. So this is a classical system.
Yeah.
And if the ball gets stuck in one valley, it's stuck in that valley. You'd have to come and pick it up or kick it or inject energy to move it to the other valley. And that's true on average in a quantum system, but not completely. And so, on a sort of statistical basis,
Mm.
if your quantum ball is stuck in one of those wells, it can uh, eventually move across to the other well without having to have that additional energy to get over the bump.
Mm.
And so then if you imagine it in this computer, right, you know, a one is a collection of charge and a
Hmm.
zero is no charge. And so
Yes.
you have these, obviously this is very schematic, but you have these, you know, bundles of charge in your semiconductor. And if the wells are too close, then charge in one can start appearing in the other, and then that
Mm.
ruins your computer.
Yes. I've seen a more surreal explanation that used to appeal to me to get across the weirdness of that, because that doesn't, I think that's totally accurate and more fair than what I'm about to say. What I'm about to say is a bit more metaphorical. But it got the idea of the weirdness across. So the suggestion was if you have pebbles and you have a window and the window's closed and you throw them against the glass not strong enough to break it, then most of the pebbles will just bounce off. But in a quantum world, some of them will disappear on this side and reappear on the other side and get through without breaking the glass. And that's
Yes.
quantum tunneling.
Yes. Yes. Yeah. No, that's true. Um,
And that's weirder, even though it's exactly the same.
it is weird. It is weird. Yeah, this is one of the things humans are really bad at dealing with large numbers because what you're
Mm,
saying there is that quantum is inherently probabilistic. And
yes.
so there is a non-zero probability that no interaction will happen.
Mm,
It's only because, pebbles and glass have however many billions of atoms,
yes.
maybe billion, maybe millions, who knows?
Mm.
Um, that these large numbers make that probability possible. But yeah, that there is a non-zero probability that that will happen.
And some of the problem there is that it's not just the energy that is uncertain, it's the locations, which is why some of the pebbles, might not, well, we could say some of the pebbles might acquire the energy suddenly to break the glass when you didn't expect them to. But other ones will just literally disappear and reappear because the uncertainty in their location increased. And suddenly they're on the other side.
Yes, so this is the Heisenberg uncertainty principle,
Mm,
um, as it's called, which says that you can only know the position or the momentum, so think speed, to arbitrary precision, and that the better you know one, the less well you know the other. Um, yes. Now this is again one of those things that's up for debate because what does it mean to know, right? Does a human have observed it? Well, surely not. That makes it feel like humans are too special. So
mm.
then does some apparatus just have to have observed it? And is an observation just it has to have interacted with a particle? Well, what about all these photons streaming through us all the time?
Yeah.
This is one of those things. I mean, it's uh,
Yeah. Well, you could say that the faster you go, the less you know where you are, and the more certain you
yeah.
are where you are, the less you're moving.
This is true. This is true. This is true.
But
There's a
yes,
lot.
that is so what you've got down to there is the interpretation of quantum physics. I think this is one of the central mysteries, is that, and I think that's where probably why the double slit experiment can be an important one for people to do. And I know there's Derek Muller, who has the Veritasium YouTube channel, who's done
Mm.
all sorts of TV shows. Um, he actually got a portable version of the double slit experiment that he built and carried it around to beaches around Sydney and asked people what they thought they would see and then got
Yeah.
them to have a look because their intuitions don't match up with what they actually get. But the interpretation makes all the difference. I think this is one of the central mysteries that there's multiple interpretations of what the observations and the calculations mean. So the calculations give us predictions, and the observations tell us that so far the maths is really good. But what it all means so that we can predict how to use it and predict further physics is still up for grabs. So we've got multi-worlds theories, we've got all sorts of things saying, well, the probability calculation, the wave function collapses in this way, and we get certainty this way or certainty that way. But we don't really know. And every time we do an experiment, it doesn't tell us the answer. It tells us the answer, but not which interpretation is right.
Yes. Yes. So this is um, something that physicists deal with a lot.
Mm,
It the general consensus is that in physics we care about observables, so we care about things we can measure, and we care. A theory is good if it predicts observables correctly, and anything beyond that is not really a physics question. It's a
mm.
philosophical question. Maybe very interesting. A lot of them are. Um, but they're not physics questions. And I think that's an important, when you're doing physics, that's an
Mm,
important line you've got to draw in the sand. Otherwise, you end up in these infinite spirals, um, uh, where, some of these questions, there may never be an answer.
mm.
Maybe it doesn't. Who's to say that we're ever meant to know how it's working,
But
right?
I mean, this is the philosophical argument, I guess, is that from one perspective, in order to be able to make new physics or new science, in order to be able to understand something well enough to perhaps build a device or come up with a newer theory, you have to be able to sort of have a visualization and a intuitive understanding of what's really going on, a picture in your mind, a usable metaphor of what's going on is one argument to be able to build new electronics or predict what's going to happen or just be able to make testable predictions. Whereas what you're talking about there, I think, was it Heisenberg that came up with shut up and calculate? That you shouldn't. Somebody had that line that
Yeah, it
don't
sounds
worry
rather
about what it
Heisenberg.
means, just do the maths, make your
Yeah.
observations, and don't worry about trying to think with your pretty little head.
Yeah, I think that would have been Heisenberg. That sounds very Heisenberg-esque. Um, yeah, look, you're right. I mean, uh, at the end of the day, we do need to progress, and this sort of shut up and calculate um, would work fine if you had infinite time and infinite resources to try everything. Um, yeah, and so I think actually this brings up an interesting point. I think this is
Mm,
kind of art in physics
yes.
uh, that is often misunderstood. I think it was Feynman who said that people often say that physicists or mathematicians aren't very creative. And he said, in actual fact, we're some of the most creative people in the world because we have limits to what our creativity can be because we need to describe the physical world. So we have rules. And we have all this creativity to make up a system that results in the things we observe.
Mm.
So I think you're right. And I think that's the art of a good physicist is having that intuition as to what would be worthwhile to calculate.
Yes, yes, because otherwise you can't really do anything much. Now, support diffusion by buying from the Diffusion Science Etsy store. Catch people's eyes like flies. I have Hawaiian shirts, t-shirts, pullovers and mugs with many different Venus flytrap designs based on my photographs. Check out the shirts and other Venus flytrap designs at diffusionscience.etsy.com. I'm Ian Wolfe. Yes, I think there is a lot of creativity in physics where I know a lot of people think that it's all just maths and it's all been discovered, but you need a very vivid imagination and a very flexible way of thinking to be able to do any of it.
Yes. Yes, very much so. Very much so. Flexibility is a great word there too, I think. I think this was, if you look at the history of how quantum developed, there was very much a generational struggle in the early physicists of the young Dirac and Heisenberg and Pauli wanting to bring into this new world, this new quantum world, and
Mm.
your Einsteins and uh, even your Sommerfelds were kind of like, oh no, that's not how we did physics,
Mm.
There's a famous EPR paper. It's called Einstein. Oh, gee.
Einstein, Podolsky, and Rosen.
Podolsky. That's it. That's the one. Yes. Um, they wrote this paper uh, talking about the so-called hidden variables,
Yes.
which is basically the idea that there's we can't have a world built on chance, so there must be something that we don't know about that we're sort of approximating with chance. Um, but that I mean, again, this is the kind of interpretation that you can never actually prove wrong.
Well, no, I thought they'd gotten very close to almost proving that hidden variable theory wasn't right
Oh,
with some of those experiments
oh,
because they've done the EPR experiments, Clauser and Aspect and all those people that came afterwards. They've got closer and closer to doing those experiments and narrowing a tiny bit how you can interpret quantum physics. And the interesting thing, I think, is that hidden variable theory, which says that there's a secret set of rules under the world, is magical, is the magical universe, right? So the universe of fantasy and mysticism and religion says that the world you see, the world you observe, isn't the real world, that there's secret rules underneath. And if you just manipulate those rules, you can do what seems to be impossible. And that's a hidden variable theory, straight out a hidden variable theory. And if you could
yes.
prove that hidden variable theory was true or not true, that would rule in or rule out that sort of interpretation. And I thought they hadn't got an absolute ruling out, but I thought they got very close.
So
Um,
you're
yeah.
right. You're right. So this is the you can do things like the Bell's inequality
Yes, exactly. That's what I was
experiment.
trying to think of. That's hard to
Um,
explain to people.
yeah. Uh, so
You need a good metaphor.
the Bell's inequality experiments. They're basically proving that um, information can't travel faster than the speed of light. And so the idea would be that if you had a hidden variable, um, uh, then it would have to transfer that information between two measurements faster than the speed of light, um, if it were there. Otherwise, we have to believe this sort of quantum probabilistic um,
Mhm.
nature.
Right.
Uh, now, I must admit, I'm not completely familiar with these experiments. I should go and check them again to see exactly what they claim. But I think you're right. I think they may have actually claimed quite strongly that you can't have these hidden variables. Um, that's a good point. Maybe I should go back and check on these.
I'll have to make a list of things I should cover that in the show as well. I thought it was interesting because it's one of those things that, as I say, is related to people's thought for long periods of time of history that this might be the way the world works. So if that's something we could ultimately test, that would be interesting.
Yes, yes, very interesting. It would.
So we've got
Um,
5 minutes left. Um, I was thinking if you are happy to go to another, do you have time for another Zoom session if we
yeah,
start
yeah,
again?
yeah. I'm happy to
Um,
keep going.
so we can do that at the end of this. I just thought I'd check with you. Is there anything you'd like me to rather than just generally talking about quantum stuff this way? Did you want me to focus in on stuff you're doing with your own PhD research or anything like that?
Um, look, I'm really happy with whatever. I'm.
Because I know you're preparing a talk, and I don't know whether you had things in mind you wanted to discuss from that. It might give you some practice, or some
Oh, look,
advertising, something.
the talk is basically this. It's just, I think there'll be a bit on the history of quantum,
Mm.
bit on. Actually, there's this nice little demo I can do with polarizers. I don't know how well it will work through a camera, but
Oh no, and then there's whether we can get it to be explained well enough on radio.
that's true.
Because
That's
the
true.
most of the audience will be audio, some of them will be
Yes.
on YouTube. But geez, it's a good
Oh, well, that's it.
experiment. If you can maybe describe not just what you're doing, but what you see as a result, that might get
Yeah.
it across to people because they can try it themselves in Science Week.
Yes, they can. They certainly can. Yeah.
Such a good experiment. I remember being really surprised by that when I was in high school.
Ah, yes, yes.
The
Yeah, no, it is.
first
It
time we
is good.
saw it. Because it's so unintuitive. It shouldn't work.
It
It
is.
shouldn't work.
It is. It's one of those, like, preparing this talk, I'm sitting down, I did the maths,
Mm,
and, I can believe the maths. That's fine. But then I was thinking, how in the world do I explain this to people without doing the maths for them?
and that's the
It's weird,
challenge.
bizarre. Yeah, yeah. So
Absolutely. So, because then first you've got to explain what a polarizer is and what
yeah,
polarizing of light is. So that's a new. two new concepts to get across. And then once they're comfortable with that, then you can start saying what happens when you put them at different angles.
Yes, 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 this is right.
And I think the people who will be good physicists are the ones who will be more offended at what's happening.
Yes.
Because if you just say, oh, yeah, sure, that's what happens, okay, it means you haven't really internalized anything.
No, that's a very good point, actually. Yes. Yes. It should hurt your brain. Yes.
Mm,
Basically, the idea is these polarizing lenses,
mm. Like
um,
Polaroid glasses.
exactly like polarizing glasses. So I have a pair of those here. Um, and you have light. So light is a wave, so it wiggles and it can wiggle in a direction. And a polarizer, they call them polarizing filters. I think filters is a confusing word, but anyway. So you have wiggling light and it can only wiggle in one direction. This polarizer, let's say that it's wiggling up and down. And then the same thing here. If I put them that way, so they're aligned, then the light coming through the first one can keep wiggling in the same direction and go through the second one. If I put them at 90 degrees, then it gets completely blacked out. Oh, that looks all right.
Yeah, that looks very good. So it's black.
Completely black. So because the light coming through the first one is wiggling up and down, the second one only will allow the light wiggling side to side.
Nothing comes through.
Nothing comes through. And then if you take a third polarizing filter, I'm using
We're
sunglasses.
about to get cut off. Hello, welcome back.
Hello. Yes.
So you were showing us what happened when you had an upward polarizer and a horizontal polarizer together and you got black.
Yes. So here we go. That's them.
Hmm. And if you rotate one of them, oh no, you've got some sunglasses as well.
I've got some sunglasses, so hopefully I've got enough dexterity to do this. We can get the sunglasses in the middle,
Yes.
or maybe I need to go this way. So I can see it from where I am, but I'm not sure how good it's coming through on there.
It's not quite. Can you see it on your screen that at the moment
Yeah.
one side still looks black and the other side looks clear?
Oh, that's a bit tragic. Oh, well, it's worth a try. What if I use one last attempt? What if I use this? So that should be, yeah,
Yes,
see through, and then it's dark.
that's correct.
And then if I get it that way, if I get this one at 45 degrees,
Yep. Oh, if you show a little bit of the white wall behind them a little bit more, and then
there you
rotate
go.
it again, rotate it so you can see the difference. Yeah, that's it. So it's totally, and then it's,
Yeah,
mm.
there we go. All right.
So what's happening?
Okay.
How would you describe that?
So this is okay. So this is what I said before. I think filter is a misleading word. If we think filter classically, then we think the first one is filtering out everything that's not vertical, and then the second one was filtering out everything that's not horizontal, so there's nothing left. Okay, so if we put a third filter in, we would think we're filtering it more, therefore it shouldn't let any more light through. It should be the same if we've got nothing left at the end.
Of course.
But of course, that's not what happens, right? If we see this third polarizer at 45 degrees in between, then we see light come through. So, okay, so we have to get rid of this idea of filtering. We're not filtering anything. Instead, what we're doing is we're making use of this idea of superposition, which is it's a fancy word. It just means two things in the same place, superposition, and they add together. And so when we had this vertical light coming through the first one, and then we put a polarizer, so if you imagine putting your hand at 45 degrees. Now that vertical light can be made up of two perpendicular waves. Okay, one of them in the direction of this 45-degree polarizer and one perpendicular to that. So that vertical light has a component in that 45-degree angle. And then we now have this sort of angled light, this diagonal light, and then we hit the next polarizer, which is at 45 degrees, and the same thing happens. We can now break that light into a new set of two lights that has a component in that horizontal. And so it turns out, if you go through the maths, that the intensity of light at the end of the three is 1/4 of what it was when it went in at the start. So it gets rid of some of the light. It is filtering in that sense, but not all of the light. And you could imagine that if you kept putting in more polarizers at smaller and smaller angles, so that you would then had an infinite amount of polarizers, each, an infinitesimal rotation.
Yes.
Then you could sort of bend the light the whole way through without dimming it at all.
And I think that's part of the unintuitive part of it, is that, as you say, it's not merely blocking some of the light and therefore just filtering it, which is when you just got the two, that's what it's like. But when you've got your ones at 45 degrees there, as you say, you're bending it. And that's amazing. That's not what you would expect at all, that you can just bend it and change what you measure that comes out. Not just if you were to put a detector, a polarizing detector or another filter, you would find that not only did some light get through, but it's at a different direction to what the first filter had made it go or detected. Or say the first filter is purely vertical. What comes out is not vertically polarized light, because by putting those extra filters in at different 45-degree angles, you've bent it.
Bent it, yes, yes. So I think this is a much better interpretation than saying filter.
It's almost like a lens for polarizing.
Yes, yes, you could say that. Actually, the there is a shrimp.
Ah, the mantis shrimp?
Mantis shrimp, that's it. And it has lenses in its eyes that can see, I forget the number, but it's something
12.
like 12. There you go, 12. Order 10. Um, 12 different polarizations.
It's just
Of
amazing, isn't it? And they can see so many extra colors, I believe, as well.
yes, yes, I think so. Yeah.
Mm. No,
Um,
people should Google mantis shrimp, because they also have the ability to create a sonic boom underwater as a hunting weapon.
yes, yes. They are crazy animals.
Yes,
Crazy.
yes, worth a look. The other thing that's gone quietly on that used to be a big thing was, of course, quantum computers, and it turned
Mm.
out to be a very big project. So that they've been trying to make a practical one that does more than a few qubits worth of calculation for over 20 years. And in UNSW, they've done it in silicon, which
Hmm.
is quite
Hmm.
amazing. Um, how would you get across what quantum computers are to someone that's not familiar with anything more than their desktop or laptop or their phone?
Yes, yes, this is a good question. I have been asked many times.
Mm.
Often when you say to someone that you meet, I'm a physicist, it's one of the first questions that comes back. Which is good. So a quantum computer is maybe first I should say a classical computer, the computer that you work on every day, um, runs on bits. So a bit is it's a value. It's either one or zero, representing a on or off, a yes or a no. Um, and then you can do calculations with these bits. Now, and if you want to do more calculations faster, you basically just get more wires to represent. If a wire's on, it's a one. If it's off, it's a zero. You get more wires so that you can do more bits at once, and you scale this way. Now, with a quantum computer, it uses these so-called qubits, quantum bits. And the idea, the hand wavy idea, is that it can be a one or a zero or somewhere in between. So it's a superposition of these two states. Just like before we saw with the polarizers, that the vertical light you can represent as a superposition of sort of the two diagonals added together. And then, depending on how you set up your device to observe this qubit, you could imagine it's a polarizer. It's probably an inefficient way to do it, but you could, in principle, have a beam of light that is your qubit, and then somehow you just have to chase this beam of light as it travels around. And you could measure it with polarizer, and you have this probabilistic mechanism that will mean that it will, when you observe it, it'll move to one of the two states. This is the basic idea. There are lots of different ways you can make this system in practice. And then there's a whole bunch of different quantum computing algorithms that is basically the mathematical machinery to go from, well, what we observe, what can we infer from it? And you can do calculations that you can't do, or at least calculations scale differently on a quantum computer. So the great example of that is almost all encryption relies on finding the prime factors of a very big number, which there's no algorithm to do. You have to do guess and check, which is quite easy for small numbers, but very difficult for very large numbers. And it works as encryption because nobody has a classical computer big enough to do the guess and check, to brute force it. But a quantum computer could, loosely speaking, could do all of the guessing and checking in one step. It could test all the states at once. And then depending on which... Sorry, say again?
With superposition?
With superposition, exactly. And then get your outcome almost instantly. So this is the idea. Now, the problem they've had is because you can imagine this sort of superposition state it's a sum, quite literally a sum of all these different states, then any noise you get into your system, so whether that be, depending on what physical system you've got, maybe a truck drove past and there was a vibration, and now all of a sudden, your molecules have picked up this part of this state into their superposition, or maybe the laser you used, had some uncertainty, and over time, it's spun these atoms around, whatever the system is. It's very hard to maintain the sort of purity of these qubits against all this noise. And this just kills the efficiency of quantum computers. Now, of course, they're improving this over time. They want to get more qubits together. And then the more qubits you have, the harder it is to keep them all pure. These are really engineering problems. Yeah. So as far as I know, we've not really had a quantum computer that is better than a classical computer. There have been lots of claims of it. Quantum advantage is the term they use.
And quantum supremacy?
And quantum supremacy, yes, this is also a term they use. Yeah. So it's kind of this waiting game of who can be the first person to, I suppose, choose a physical system that is easier to, and then once you've done that, actually handle all of this noise.
And of course, that encryption is the basis of all banking and password protection and basically almost everything we do online.
This is true. So, most governments around the world, most of the major governments around the world are very concerned about this and putting a lot of money into it. But it also comes with some positives for encryption, because you can do these sort of new quantum encryption algorithms. They have this phrase quantum key distribution, where I don't know. I probably shouldn't go into too much detail. I'm not an expert, but there are algorithms sort of built on this new quantum system that would also be secure. So
Mm.
it's not like everything breaks, right?
No, no, no. But it
We have
changes a lot of things. We have to change a lot of things.
we have to
But
change a lot.
there's a couple of levels of things. So on the one hand, you've got quantum computers being able to do things that would take classical computers billions of trillions of years they can do very quickly.
Yes.
And that's one of the things that's hard, I found, to get across to people, that quantum computers can be exponentially faster than classical computers. And then you've got to try and get across that that means not a million or a billion or a trillion times faster, but maybe 10 with 10 zeros after it faster or more.
Yes.
It's just ludicrously fast, which means that a whole lot of things that at the moment are too hard because they take too long with too much power or too much computation power could be done almost effortlessly. And that can change everything, really.
It can. It can. Um, yes. Yes. And it's a very interesting world. Um, but the other thing to remember too is that I I I don't think we'll ever have like a personal quantum computer. Um, because there are plenty of things that classical computers are just fine for, right? Like surfing the web and browsing emails. We've got that, right? We don't need to improve our computing power on a sort of day-to-day personal level. Um, and because then a lot of these quantum computers, you need a classical computer to sort of to control and interface with it. Um, anyhow, so
So
yeah.
then maybe they'd work together the way GPU and a CPU work together. So if you want to do your AI machine learning sort of things, you might need the equivalent of a parallel processing GPU with outrageous numbers of cores and memory. But to talk to your user and do anything with the results, you might need just an ordinary CPU.
Yeah, I think that's a good way of looking at it. Yeah, yeah, yeah.
But then
Um,
we've also got, oh, I wish I could remember the details. Another thing for me to look up. You may have heard of this or not, it's not so well known. There's some quantum algorithms that people have managed to translate for classical computers, like inspired by the way they work on quantum computers, that actually let them do some things faster because it's better maths.
yes, so there's again, I'm not an expert on this sort of thing, but it is I tangentially am aware. In mathematics, they have this categorization of N and NP. Was it P and NP? Oh, it
You're
might be
talking
P and
about
N.
non-polynomial time problems, is that it? Or is
Yes,
that something
yes.
else?
No, 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 no. I'm pretty sure that it is. So you have polynomial time and non-polynomial time problems, which is basically problems we can solve in a reasonable amount of time and problems we can't. Uh, and there's been this ongoing debate as to what is like where's the boundary between the two. Um, so I don't know what the latest uh, verdict is, but I think this idea of what you're saying, if people used to think that there was a clean line, and then they developed all of these quantum algorithms for quantum computers, and then somebody thought, oh, but hang on, actually we can do that classically as well, and all of a sudden the mathematicians aren't quite sure how to draw this, um, how to categorize problems into these two things, which is very interesting and a little bit exciting because maybe there are some problems that we've always thought would be too difficult to solve, but we just have never thought of the right way to go about them.
Mm. Well, this seems to be one of the things that's making greater strides than even the engineering now. For a long time, it was the engineering and computing, but it seems that it's the mathematicians and the academics coming up with new ways of solving problems, new types of maths in a way. Like I remember seeing back only, in the deep, dark, distant past of 3, 4 years ago, that AI was not very good, but even generative AI, the images looked like nightmares and
Mm.
the chatbots weren't very good, and OpenAI was getting nowhere. And then somebody came up with transformer mathematics, and that got applied to machine learning, and suddenly it was all boosted up to being useful. Suddenly ChatGPT worked, and Stable Diffusion was able to generate images that looked good, and Midjourney and all the others, everybody that's come after it in the last 3, 4 years. And it's all based on, these mathematics that came out of universities, not from corporations. And it's all different ways of looking at mathematics and applying it to all these things. And then suddenly there's a million uses. And so it's not always just the limits of how small the chips are or what the underlying hardware is.
No, no, that's right. That's right. Um, it's these sort of these shifts in the way of approaching a problem. Your
Mm.
term can
And my understanding is that quantum encryption, which is my way of looking at it, is in classical encryption, one of the ways you could do is what they call a one-time pad, where you've got a little book of random numbers that is exactly a copy of a second book of random numbers, and you send that off in the post or physically to whoever you're going to talk to secretly, and you each look at one page for the day, and you rip off that page and you use that random number and then throw it away, and then you have another one for the next day. And as long as your random numbers are the same, nobody can break your encryption because nobody knows what the random numbers are if they're genuinely random. And in quantum encryption, I believe you can get two entangled systems that spit out the same random numbers because they're correlated because they're entangled. And so you can base encryption off that. But the thing, and I know that they're doing that on real physical optical networks now, it's not clear to people. Would you have any idea of how to explain why that's useful? Or would it be better to try and explain what entanglement is?
Well, so one thing I can say that I do know about these um, quantum encryption algorithms is that they can also detect if there's a third party, like an eavesdropper, because observation changes the state of the system.
Mm.
It would be like, in the classical sense, if somebody read your book of numbers, it scrambled itself, and then you would see scrambled numbers and say, "Oh no, somebody's read this." Um, so uh, maybe it's worth going a little bit into entanglement because this is another buzzword of quantum. Um, the idea is, so again, going back to superposition. Uh, let's say we have one particle and it has we use spin, doesn't really matter what spin is, just a property of the
It's got a
particle,
property called spin. Yep.
and it can be either up or down. Now, if you have two particles, then you could have, one up, the other down, vice versa, or they can both be the same. Now, you can actually make a superposition state where you have one of them's up, the other's down, plus the inverse, the other one up and the first one down. And that together forms a superposition state, and you can't separate that into a state of you can't separate that into two independent particles. So these particles are now entangled because the state of one reflects the state of the other.
So you've got one equation that really tells you about as if they were one thing.
Yes, yeah, the physical state is a combination of these options. And so these particles are now entangled. And then because it's quantum, if you're not observing anything, it's all probabilistic. But as soon as you make an observation, you know something about one of the particles, and because the physical state is the combination, then necessarily the other particle has to be, if one's up, the other's down, however it's set up in the state. Because that's the physical state. And so in this way, you can make these entangled particles with the entangled photons, and then you can separate them over long distances and these can be your sort of keys. And again, there's quantum algorithms as to exactly how it works, but you can imagine that these are then kind of like the same key split across two different positions.
Mm.
And then if somebody else ever tries to observe your key, to observe what sort of key you have, then the quantum state will collapse. It's the term. You've made a measurement. And then everybody with that key will be able to see that somebody's measured it. And so you can send out a new key. And so in a way, you could make this system of encryption that you don't actually even need to encrypt it. You can just constantly be seeing if anybody's reading it. And if somebody does read it, then you can, change the message you're sending or whatever.
Yeah, so you can detect if someone's intercepting you or trying to hack to get the information.
Yes. Yeah. Yeah.
No, it's quite impressive. And of course, I guess, one of the things is that entanglement. Whoops, that entanglement is important with quantum computers as well, because isn't that you you're putting the quantum system in your computer into superposition, and then all of the states interact, and when you observe, everything but the right answer cancels out.
Yeah, that's the idea. Yeah, that is the idea. If you can, yes, you can set it up correctly such that the thing you observe should be the most probable answer.
Yes, and if it's not right the first time, you can do it again.
You can do it again. That's right. You can get statistics is the phrase. Do it lots of times. Um, and then of course, this is one of the other problems they face is you've got to design your system well enough such that the most probable answer is more probable enough that you can detect it and it stands out.
Mm.
But again, these are engineering problems which I'm sure will be improved over time.
Well, this is one of those things. I've noticed that there's people offering courses and tutorials online to teach you programming quantum computers, and you wouldn't have thought they were advanced enough. I think are there a lot, do you know about quantum computing programming languages?
So I know a very small bit,
Hmm.
which is that in my undergraduate, one of our laboratory practicals classes was that we logged into, I think it was Bell Labs. No,
IBM?
IBM. It'd be IBM. Yeah.
Okay.
And you could log in. They have a quantum computer. I think it's, I don't know, order 10 qubits or something like that. It's pretty small. But it is a quantum computer, and you can log in and you can uh, um, program it. You can set up these states on, I think from memory, there were maybe four qubits. And, you can set up things like an initial condition, start with, whatever spin oriented in this way. And then there are different, most of these systems work by you shine a laser at it and that interacts with the spin and that can change it. And so you can, do these little pulse diagrams, which is just turn the laser on for this many milliseconds. And we could sort of do this. So it's not programming, as far as I'm aware, there's not programming as in you type text like you do. But you can do these sort of, you're basically programming a laser. That's what you're doing. To turn on and off at specific frequencies to manipulate spins. Yeah, beyond that, I don't know. This isn't really what I work on. But
No, that's fair. Well, that brings us to what you do work on. So what is it that you're working on?
So I work on particle physics. So in particular, I'm interested in neutrinos at the moment. So neutrinos are a very fun particle. They in our standard model, so think like the periodic table, but for particles. Neutrinos, every electron has a neutrino sort of buddy. And neutrinos are neutrally charged, as you could guess from the name. And uh, have a very small mass, um, and they only interact with the so-called weak force, which means that they're very difficult to detect because they almost don't interact at all. Okay, so recently being 50 odd years, we've detected them, and more recently being, I don't know, 10 to 20 years, we've detected neutrino mixing, which has raised alarm bells because we said they didn't have mass. We said their mass was zero.
Yes.
But this mixing means that they do have a mass, a very small, but a non-zero mass. And so now there's this open question of, clearly our standard model is wrong because it says neutrinos have zero mass. So we need a new model, which in practice would just be a slight variation of the standard model that gives them mass. And this is ultimately the question I'm working on. How do these neutrinos get their mass?
Mm.
And, as a theorist, as I think I said earlier, there are lots of beautiful theories that do the job well. So it's a game of whack-a-mole, really, as new experimental data pops up. It's like, okay, what does that rule out? What is still allowed? And so forth.
And so is that something you're doing by experiment, or is it mainly you're working on the theory, or a bit of both?
No, I'm a theorist through and through. So it's a lot of thinking and doing maths on my end.
Mm.
And then, the experiments are these huge, huge collaborations. And they write a paper and put up some data, and then we try and fit our models to that data. It's basically the workflow.
But you'll at some point be making predictions that they'll have to test.
Yes, hopefully. Hopefully, that would be great. Yeah, it is, sometimes theory comes first, sometimes the experiment comes first. It's this real sort of beautiful dance in physics. And
Yeah.
in the case of neutrinos, the experiment saw it first.
So how did this particular problem grab your attention?
Well, I suspect, like many PhD candidates, I knew I wanted to do something in particle physics, particularly because I really like field theory, quantum field theory. I just think it's beautiful maths. So I wanted to do something that I had a look around. I found my supervisor, and this was one of the projects he was working on. And I said, that sounds fun. And so here I am. I think I would have been equally happy on any sort of particle physics problem. I think they're all very, very interesting.
That's
Um,
fair. Well, I think, I don't know. Well, I'll try you on a little bonus question.
sure,
Something that
sure.
you, now, I'm sure you're familiar with the Casimir effect. Yeah, where
Ah,
you've got two
yes,
metal
yes.
plates, you bring them very close together in a quantum sort of sense so that there's actually less space between them than there are wavelengths of light that can go there. So you're excluding some wavelengths of light between them. And if you
Yeah.
do that, um, then you can get an electrostatic force that brings them together, and you actually sneakily get a tiny, tiny amount of energy out of the vacuum for nothing. But that interested me. But what I found was about quite a while ago, maybe 15 years ago, somebody thought if we put a particular type of material, a metamaterial, between these two metal plates, then if you do the field theory and just do all the maths and turn the handle, instead of getting an attractive force, you get a repellent force. Now, that was good for the field theorists, but for people like me that were raised on the standard model, I had to translate it in my head back to the standard model. So with Casimir effect in the standard model, what's happening is because you're excluding some wavelengths of light, then the virtual particles in the general vacuum of space around you, or just around you, there's more of them than there are between the plates, and that's what pushes them together. There's less nothing between the plates. because there's less virtual light because wavelengths are excluded.
Mhm.
But when you put the metamaterial there and you get a repulsive force according to the field theory maths, if you turn that back into that idea of virtual particles and, standard model, that would have to mean there's light being produced out of the vacuum to push the plates together out of, so you're actually, I mean, either way, you're getting something for nothing in a tiny, tiny amount, which is allowed within a tiny amount. But
Mhm.
it seemed like you're getting too much, that there's extra light being produced between the plates to push them apart. Now, that's simply me turning field theory into standard model, as opposed to just trusting the maths, which is what the mathematicians have worked it out. And even the experimental physicists that were trying to get levitation effect out of it, they just trusted the maths as well. Nobody but me cared what it actually meant in the real world. But I couldn't find any physicists. I asked a couple of different physicists this, and most of them just said it's not my area,
Mhm.
which is
Mhm.
totally fair, but annoying.
Yes.
Do
Yes.
you think my interpretation of what it would mean is flawed, or it just doesn't matter because something else might be going on?
Well, I will say it's not my area, but I won't disappoint you, I hope. Um, some things that are popping up in my head. So first of all, you're talking about getting something for nothing. We talked before about the Heisenberg uncertainty principle with position and momentum. The same is true for energy and time.
Mm,
So in principle, you could get as much energy from the vacuum as you wanted, as long as it was for a sufficiently small enough time. Um, so that's one thing to consider. Now, how that works with spreading apart these plates, perhaps you only need, you know, some energy, some extra photons for a fraction of time,
mm.
and they can annihilate, and you get other photons for the next fraction of time. Maybe. I don't know.
So
I'm
maybe it's
spitballing.
just fine as long as it's really short.
Perhaps, perhaps. Um, the other thing is that when you think of uh, there being less nothing, that you're thinking of pressure, right?
Yes.
Um, I suspect one just has to be a bit careful with the pressure analogy here, because pressure is it's a property of a macroscopic system. It doesn't really make sense to talk about pressure if you're talking about individual particles. Now, the plates are a macroscopic system, so
Yes.
there's certainly some sort of pressure you can talk about. But uh, the solution to any paradox you find might be that you have to be careful about how you use the term pressure. Um, yeah, I'm sorry I don't have a more complete answer for you.
That's all right. I
That's
think
very fascinating.
I'm going to have trouble finding anyone. So when I talk to the field theory mathematicians, they're not interested in a physical explanation of that sort at all. And if you talk to anybody else, it's not their area.
Yeah,
And
yeah, hell yeah.
so it's kind of, if I was going to do a PhD, that would probably be the area I'd try and look into. Because I
Well, that's
think
very fascinating.
I
Yeah.
can't find anyone who can tell me I'm wrong in my interpretation as opposed to what's going on we'll only know by experiment and by
Mm.
proper theory. But in my translation from one realm of a physical model to a different physical model, I
Yeah.
think I got it right.
Well, look, I mean, as we touched on before, if it's useful to you, then it's an acceptable model.
Oh, well, it's only useful to me if I can do something with it. Like if I was able to do experimental physics, if I had access, if I went off and did my PhD, then I could try and do the experiments and see what happened.
Yeah, yeah,
And then
yeah.
that would be my way. I did applied physics, so I'd want to find out by doing it
Yes,
rather
right,
than just
right.
doing because the maths has already been done and it doesn't tell me enough.
Yeah, yeah. No, I totally appreciate that. That's very cool.
Well, look, I'll just quickly say, James, thank you very much. That was
Well,
really
thank you.
interesting.
study science, because you will find in the study of science a richer, more rewarding life.